The plane wave spectrum. This lecture will be a bit more mathematical than they have been, and here we're going to focus on the periodic fields that gratings induce. So we have this nice uniform plane wave, it enters a diffraction grating, and that causes the field to become periodic. And so we want to look at that in much more detail. So before that, we'll review the complex Fourier series. This is not meant to teach the complex Fourier series, but just to review what it is and put it into our mathematical framework. And that'll lead into what is called the plane wave spectrum. And anytime we have a periodic field, we can set that equal to a sum of plane waves, all at different angles. And if all those plane waves add up, they will give us that periodic field back. That's the plane wave spectrum. And we'll look at that for ruled gratings, and we'll look at that for crossed gratings. Complex Fourier series. The one-dimensional complex Fourier series is hopefully something you have seen in your mathematical background. So one thing I'm showing here is a one-dimensional function, f of x, and we notice that it repeats with some period. And I've outlined one period here, and I'm calling the period lambda x. So that function repeats every lambda x. When that is the case, we can expand that function into a complex Fourier series. So that's exactly what's happening here. Here's our periodic function f of x, and we're writing this as a summation of a bunch of terms here. And what we have is a complex exponential, so this is essentially as a sine wave or a cosine wave. And then we're multiplying it by a complex amplitude that will control the magnitude and phase of this cosine term. So we've essentially decomposed our function into a whole bunch of sines and cosines with different amplitudes and phases. The information from the function is all stored in these coefficients, A. These complex exponentials are just sort of assumed that we know what they are, and we just multiply all of them by this magical set of amplitude coefficients such that when we add up all of these sines and cosines, we get our function back. So how do we calculate that amplitude function? Well, we have an integral down here. Here's how we calculate it. And essentially what this is doing is it's weighing the original function against these complex exponentials and figuring out how much of those sines and cosines are in that periodic function and letting us know in this amplitude coefficient. Notice we're only integrating over one period. So we integrate over one period, we divide by that period, and we get those amplitude coefficients. Now, to be exact, our summation has to have an infinite number of terms. Well, on a computer, when we analyze things, we can't have an infinite number of terms. So in practice, we have to limit our summations. And so now our equation becomes approximate and there's error introduced. So what we try to do is retain enough terms that we represent that function really well, but not so much that it's taking up too much memory and it's taking a long time to calculate things. Now this is something that maybe less of you have seen, but we can generalize the concept of the complex Fourier series to represent two-dimensional functions, or in fact three-dimensional, four-dimensional, five-dimensional. I have personally only ever gone up to 3 dimensions simply because we live in a three-dimensional world, but mathematically, any number of dimensions. Here we're looking at a two-dimensional complex Fourier series. So what we see, since we have 2 dimensions, now we have a double summation. And if we look at this exponential here, this is also sometimes called the kernel, and we have 2 of these terms in here, we'll recognize that this 2 pi over lambda is actually a grating vector. And the p and the q are the integers of the summation, and of course x and y are positions. And then we have another integral for calculating our amplitude coefficients. So now we're decomposing two-dimensional functions into a set of, instead of thinking of sine waves, one-dimensional sine waves, now we're decomposing them into what are sort of planar gratings or sine waves. But if we add all of them up, multiply them by those amplitudes, add them all up, we get our two-dimensional periodic function back. The plane wave spectrum. So here's a cartoon of this field that has passed through an array of dielectric objects. So it's a periodic structure. And what we've seen is that the field takes on the same periodicity as the structure that it's passing through. Now what I'm going to do is grab a cross section. I'm going to look at the field on the other side of the device and grab that and just plot that. So we have a one-dimensional function and it's periodic and has the same period as the original periodic structure that the wave went through. From prior lectures, we talked about this Bloch's theorem or Bloch's equation. And it essentially says any time that the wave is periodic, it can be, or traveling through a periodic medium, it can be written as the product of two terms. It has this plane wave term and it has this envelope term. And really it's this envelope term that is periodic, exactly like the structure that the wave passed through, not this plane wave term. This does its own thing. This is not periodic. So any field that passes through, or any electromagnetic wave that passes through a periodic structure, has to obey this form. So if that amplitude term is periodic, that means we can expand that into a complex Fourier series. And that's exactly what we've done here. We're expanding A now instead of f of x like we did a few slides ago. But we have the same summation and we have the same integral for weighing our periodic function against these complex exponentials to calculate these amplitude terms. And so pictorially, we can kind of see that if we have some function that's not exactly like a sine wave, it's something else, we can decompose that into a whole bunch of sine waves with different amplitudes and phases. When we add them all up, we get the original function back. So just remember it's this amplitude term that's periodic. So what we can do next is we'll take this amplitude term and we will substitute in this summation for that amplitude term. So that's exactly what we've done here. We're replacing the amplitude term with our complex Fourier series. Now in our next step, we will bring this plane wave term, this other complex exponential, we'll bring that inside of the summation. The next thing we'll do is expand this dot product. So we have a beta x times x, beta y times y, and a beta z times z. And since they were all added up in the dot product, then we write that as 3 multiplied exponentials. So we've expanded that. Let's go on to the next step. So notice we have 2 exponentials that are a little bit alike. Here's a complex exponential that's multiplying an x, and another complex exponential with another x inside here. So what we're going to do is we're going to combine these 2 exponentials that have the x in the exponent. So now we have an e to the j something times x, e to the j something times y, and e to j something times z. So what we can do is we can take this first group of terms and call that k sub x. We'll take this beta y, call that k sub y, and this beta z and call it k sub z. And we can think of that as 3 components of a wave vector. And now our field can be written this way, where here's how we're defining the wave vectors of each of those. On the next slide, let's think about what this actually is. So up to now, we've taken our periodic field. It's a cross section of really a 2-dimensional field, I guess. We expanded this into the complex Fourier series. We manipulated some terms, and we ended up in a form that looks like this. If we look at this long enough, what we will see is this is a sum of plane waves, right? Here's our plane waves. It's a different plane wave for every integer m, but it's a different plane wave, and it has some complex amplitudes. That way we're controlling its magnitude and phase. So any periodic field can be represented as a bunch of plane waves, all at different angles. And of course we have to have all those plane waves overlap, but if we did that and added them all up, we would get our periodic field back. So that is the plane wave spectrum, and this in one picture is the concept. Anytime we have a periodic field, That's really the exact same thing as a bunch of plane waves at different angles. In fact, I could go into a lab, I could set up a bunch of antennas that emit waves and orient the antennas to reconstruct these angles, and maybe I dial in the amplitude and phase of each one of those. And if I pointed them at a common region, I did all the angles and stuff correctly, in that region where they all overlap, I would reconstruct any periodic field that I wanted to. This is a concept behind lithography. It's also a concept behind holographic lithography, where we project beams into a photosensitive goop and make periodic structures like photonic crystals. But it's a pretty simple concept. Periodic fields, it's really the same thing as a bunch of plane waves at different angles, and we call that our plane wave spectrum. So we're very used to now, if we're looking at diffraction gratings, we have a wave coming in and we phase match the tangential components of that wave. I'd like to talk a little bit more about the longitudinal component. How do we get that? So let's have a device and let's have a wave that's in the xz plane. So we'll just let the y component of the wave vector be 0. We just have the xz plane. And let's say we have an incoming wave. And so here would be the components, the x, y, and z components of our wave vector for that applied wave. When we phase match that into a grating, so the grating is in the direction of x, so we phase match the x component, and we write something like this. Up to now, we've been writing this 2 pi over lambda as a grating vector, but here I'm deciding to write it as a 2 pi over lambda explicitly. Now, as long as we have lossless media, all of these kx's will always be real. They may be negative, but they're going to be real. Now, what about the longitudinal component? Well, the kz component. Well, the z component we can calculate from the dispersion relation, which essentially fixes the magnitude of the wave vector. So there's no ky squared here because we set it to 0. If this was not 0, we would also have a ky squared here. But we set that to 0. We can solve this for kz, and now we get a square root of the difference of two things. Now, what happens when we have the square root of a difference? Well, there's the possibility that the argument in that square root becomes negative, and we get an imaginary number. So, two possibilities. If we have a positive number under the square root, we get a purely real kz. This is what we call our diffraction orders. This is an actual propagating wave. If the argument becomes negative, we get a purely imaginary kz. Technically, that's still a diffraction order, but it's cut off. We don't see that propagating away from the diffraction grating. And it causes some things that propagate, in the plane of the diffraction grating, but it eventually leaks out. It's an evanescent field. So those are our two possibilities. Let's talk more about phase matching into a diffraction grating. So what I'm showing here, we have a wave, normally incident wave, coming into a diffraction grating. Normal incident, so it has no transverse component. When we phase match that into a diffraction grating, which is periodic, we now know we get this infinite expansion of the x component, or the transverse component of the wave vectors. And for ours, it's in the x direction. So we have this infinite expansion of possible x components of wave vectors. Well, each one of those is phase matched into the diffraction grating individually. So we have to think of each one at a time. Let's go ahead and do that. This is what we get. And what we notice for small values of kx, remember when we were calculating the z component, we had the magnitude of the wave vector squared minus kx squared under the square root. So as long as these kx components are small enough, then we get a purely real kz, and we get propagating waves. And that's what we see down here. These lowest order few diffraction orders are our propagating waves. Now when the kx components become large enough, that makes the argument inside the square root negative, making the z component of the wave vector purely imaginary. And that's where we get this pure decay away from the interface. So these are evanescent, Those are cut off diffraction orders. They're not transporting energy or power away from the diffraction grating. So even though we have this infinite number of terms in our plane wave set of plane waves, only the lowest order few are actual propagating waves. So our plane wave spectrum is actually mostly not even plane waves, but these evanescent fields. So maybe that's a little bit goofy that we talk about it that way, but that's what it's called. Now, the number of these that actually become propagating waves, that's what depends on the period relative to the wavelength. The longer the period, the more of these will be propagating waves. And of course, the shorter the period, the fewer of these will be propagating waves. So here's the conclusions about what we've talked about. Point number one, fields in periodic media take on the same periodicity as the media that they're in. So the field itself becomes periodic. We know that anything that's periodic can be expanded into a Fourier series. So our periodic fields are expanded into a Fourier series. Well, a Fourier series is a sum of discrete things. And so it turns out each one of those discrete things is a diffraction order from the grating. And there's an infinite number of them because our Fourier series has an infinite number of terms, so there's always an infinite number of diffraction orders. But it's only the low order few of those diffraction orders that are not cut off and are actual propagating waves. And this set of diffraction orders we call the plane wave spectrum. Let's think about the plane wave spectrum from crossed gratings. Some terminology that's very confusing, so it's summarized here. We've been talking about ruled gratings. Sometimes these are called a 1D grating because they're periodic only in one dimension. They're periodic in this direction. So even though we call it a 1D grating, to simulate that requires a two-dimensional simulation because we would be looking at a cross-section of this, maybe just crossing one unit cell. So a 1D grating is really a two-dimensional device requiring a two-dimensional simulation. Over here is a crossed grating. It happens to be a hexagonal array. This would be called a 2D grating because it's periodic in two dimensions, often called a crossed grating. To simulate these, even though it's periodic in two dimensions, and we call it a 2D grating, it requires a full 3D simulation in order to analyze that. So don't confuse the 1D, 2D stuff. Our 1D grating requires a 2D analysis. Our 2D grating requires a 3D analysis. Because the 2D, 3D, 1D stuff is a little bit confusing, I tend to call the first ruled gratings and the second crossed gratings, and it eliminates confusion of the 1D, 2D, 3D stuff. So we're talking about cross grating in this section of the notes. For simplicity, we'll look at a square array. A square array of cylinders, although the shape of that does not matter for what we're talking about here. But going back to our solid state electromagnetics lecture, this periodic array is characterized by two grating vectors. I'll call one kx and the other ky. And of course it diffracts how we've seen before, diffracts in all different directions because it's a crossed grating. Now when we phase match into a crossed grating, because we have periodicity along two directions now, we have two phase matching conditions. So assuming the grating's in the xy plane, we now phase match k sub x and k sub y. And notice I'm using different integer indices. We have an m and an n here. So we have two components now that phase match into this diffraction grating. Now if this were not a square array, the directions we would choose here is not x and y. We would choose directions along the reciprocal lattice vectors of that 2D array. So we don't just have two lines of diffraction. We really have sort of this grid of diffraction orders, which we're visualizing over to the right here. So if you were to do this in computer code, for example, you might calculate kx as a one-dimensional array of m, ky is a one-dimensional array of n. You can think of that as like x and y. But really, we're talking about a two-dimensional set of components. And so in MATLAB, we would use this mesh grid command, and we would get these 2D arrays that describe the x and y wave vector components of all of these plane waves. And so that's the best visualization I've come up with of what a bunch of diffraction orders being reflected and transmitted from a cross grating might look like. What I'm not showing there are all of the cut-off plane waves that are evanescent. I guess I ran out of artistic ability when I was visualizing this. So to visualize these arrays, in principle, yeah, we calculate kx as a one-dimensional array, but actually in the physics of the device, this is really a two-dimensional array. It's just that it has no y dependence. It's only changing as a function of x, or only one array index, which is why we can write it that way. And so the ky component is the other way around. It's uniform now in x, but along y it's changing. You can also think of this as the n direction. But if we now put these together, x and y components, this is really what the expansion for the transverse components of our wave vectors for our plane wave spectrum would look like, or our diffraction orders. But that's just the transverse component, not the longitudinal component. So the longitudinal components, those are calculated from the dispersion relation. The longitudinal component for the reflected wave has a minus sign here. That's the only difference. That's because it's reflected backward and is now a backward traveling wave. But these are both still two-dimensional arrays. But since we have the square root of a difference, those z components can be purely real or purely imaginary. What is a way to visualize that? Well, we start off with our transverse wave vector expansion. And these lowest order few, the transverse component is small enough that if we look at the longitudinal components, we get purely real. However, outside of that, and again, I guess I lacked artistic ability to try to visualize that, but this is showing the purely imaginary kz components. So these are all of the cutoff diffraction orders. Only the lowest order few are actual propagating waves. And it's very common to see that type of picture. Well, not specifically the picture, but in terms of the lowest order few being just the propagating waves and the rest being evanescent. So we could look at this on the reflection side or the transmitted side. These are the two pictures that I showed. And let's put all this together. So if we combine the transverse component with the longitudinal components we calculated, here's what the reflected diffraction orders would look like. And of course, the rest of these are all cut off. They'd be little evanescent waves. But here we have our propagating waves. And so I've been sort of also drawing them this way. On the transmitted side, clearly I've put a higher refractive index here. We have a whole bunch of transmitted waves, and so much more transmitted diffraction orders than reflected. But still, at some point, the transverse components become too large even for the transmitted side, and we have evanescent diffraction orders out here. And so this mess might be visualized this way.